Hello. This chapter is about the second order circuit, and the second order circuit is any circuit that has the two storage elements, like for example L and C. So, like this one, for example, if we have L and C together, then in this case we call this second order. And the reason why we call it second order circuit is that to solve this circuit, you have to solve a second order differential equation, as we will see in this part here. This chapter is divided in three parts. The first part is talking about some initial conditions, and then after that, there's a second part which is a source-free circuit, or LC circuit, that doesn't have any source. And the last one, when it has a source, we call it step response. So this part here is about the initial condition and final condition. And the reason why we talk about the initial and final condition, because if you want to solve a second order differential equation, you need to define the initial conditions, to use them to find some constants. Usually when you solve a differential equation, you have some constants. To find these constants, you need the initial conditions. And the final conditions also are required if you need to find a step response, for example. So let's see how can we find the initial and the final values. If you have a circuit like this, usually you have a switch. This switch here was, for example, on. So this means that the switch was connected. So the source was connected to this resistor and these two branches. And suddenly you disconnect this this switch. So what happened? That now you disconnect this branch here. You disconnect the resistor, the source, and the 4 ohm resistor. So you will have this circuit only, this part only. So the initial condition is the voltage across the capacitor and the current in the inductor at the time of switching. What will happen at the time of switching? This is the initial condition. Usually we use this 0 plus, sorry, 0 plus and 0 minus. 0 plus and 0 minus is just after and just before switching. So they're supposed to be the same. So we need the initial conditions, I0 and V0. And we need also the differentiation, the first derivative of the current and the voltage, di by dt and dv by dt. And when you say I and V, this means the current in the inductor and V across the capacitor. I infinity and V infinity are the final values for the current and voltage. Okay, so this is, as I said, V denotes VC, so you don't have to write VC, but V means VC, I means IL. And usually in any problem, I will give you the polarities of the voltage and also the direction of the current. So you have to stick with it. This is a very important rule, that IL and VC will not change suddenly. So assume that you have a capacitor, for example, and you charge this capacitor to 10 volt. Then when you turn off the switch or you change the status of the switch, the 10 volt will not be 0 suddenly. It will stay 10 0, and then after that will change gradually. Will not change abruptly or suddenly as mentioned here. Okay, so IL and VC will not change suddenly when you just change the switch. So what happened here is that, for example, if you want to calculate V of 0, then this means that you just need to calculate the voltage across the capacitor when the switch was on. Okay, so in this case, the capacitor was open circuit and the inductor was short circuit. You calculate the current in the inductor and the voltage across the capacitor. And then when you turn off the switch, the current and the voltage will remain the same. This is the initial voltage. This is the initial voltage. So this is how you calculate I0 and V0. For di by dt and dv by dt, you need to get them from the relations that we know. We know that VL, for example, what is VL? VL is L di by dt. VL is L di by dt. And IC is what? Is C dv by dt. So if you want to find dv by dt, find it from IC. dv by dt from IC and divided by C. And the I by dt, find it from VL. Find VL and divide it by L. This will give you the I by dt and the V by dt. Then the final value, of course, this is a final value. So if you leave the circuit for a long time, this is a final value. So imagine that you have, for example, your cell phone and you are charging the cell phone, and your battery is 12 volt, for example. Okay, so suddenly you disconnect the power, so you stop charging it. So now what is the initial value of the voltage across your battery? It's 12 volt. It's 12 volt. So this is the initial value. Okay, what's the final value? The final value, when you use your cell phone for a long time, okay, you will have a certain voltage across your battery. What is the expected voltage across your cell phone after you leave it for a long time? It's supposed to be 0. It will die after a long time. If you leave it, for example, for a while, then in this case, or use it for 10 hours, 20 hours, depending on your how you use a cell phone, so it will die. So the voltage across the battery will be 0. So this is what's expected. If it is not connected to source, the voltage will be 0 and the current will be 0. So for example, this circuit here, if you look at this circuit, what is the final value for V and what is the final value for the current? It's supposed to be 0. Okay, initially it has certain value, of course. They have certain values, but finally they will be 0. Why? Because this circuit is not connected to any source. So finally the voltage and current will be 0. Okay. So let's take some example for this initial and final values.